Let's start with converting from 32-bit standard to decimal number representation. Okay, so this is we are continuing from IEEE 754 standard, 32-bit standard. So let's convert this to decimal number system. So first of all, what we have to do is check for the sign bit. Sign bit states that it is zero. So the sign bit is zero means it is a positive number. Okay, it's a positive number. Great. Now we have to look at the other 8 bits. Since this is 82 bits representation, 8 bits are allocated for exponent. So what is the number represented by exponent bits? Well, the number represented by exponent bits is equal to 128, no 64, no 32, no 16, no 8. There is a 4, there is a 1. So it is 133, which means after anti-biasing, if we reverse the process of anti-biasing, we know since this is 32-bit system, we have 8 exponents bit. According to the biasing, we added 128 to this. So we have to subtract according to biasing. So it will be equals to 6. Okay, so the power is 6, which means the number will be positive some, well, 1 point, some sort of mantissa into 2 to the power 6. That's the number. So now we are going to focus on mantissa. What is the mantissa given here? Well, the mantissa is 0, 1, 0, 1, 1, 1, 1, 1, and then all zeros. So the mantissa is given as 0.0101, 1, 1, 1, 1. So this will be equals to 0, 1, 0, 1, and then 1, 1, 1, 1. So if I multiply it by 2 to the power 6, that will give me positive 1, 1, 2, 3, 4, 5, 6. So it will be 0, 1, 0, 1, 1, 1.11. So this is the number that we have to convert from binary to decimal. Okay, and that decimal number is what represented by using this specific 32-bit standard of IEEE 754 standard. Okay, the floating point representation. So what is this number? Well, when we are converting from binary to decimal, first of all we'll look at the integer. Integer is given as 1 0 1 0 1 1 1. Okay, so 1 2 3 3 7, no 8, so 23 plus 64, 87. So this is equals to 87, and 0.11 will be equals to 1 into 2 to the power minus 1 and 1 into 2 to the power minus 2. So which will be equals to 0.5 plus 0.25. So the answer will be 0.75. So what's the final answer? This is equals to positive 87 point, a positive 87.75. Okay, so this is how you have to do this question. Okay, let's say we have something like this. In this question, how can we do this? Okay, well, first of all, we have to look at the first bit. So the first bit is given as 1. So the sign bit is 1, which means it is a negative number. So first of all, we have found out that it is a negative number. Then we have to look at the exponent part. Well, the exponent bits represent the number 128, 64, 32, 16, 8. So it is equals to 136. Okay, so after the reverse of biasing, we will get 136 minus 127, which is equals to 9. Okay, so let's erase this. Yeah, then well, we have to put another 0 here. Yeah, that's better. Now we'll continue the question. So next we have to check the mantissa part. So the mantissa part is given as 0 0 1 1 1 0 1 0 1 1 1 1. So it will be 0 0 1 1 1 0 1 0 1 1 1 1. This is the mantissa part. So what is the number represented here? Well, it will be 1.00111 0101 111 into 2 to the power 9. So this is equals to if I bring 9 digits in front of this floating point or the fixed point, I will get I think we have to go onto here. So 10011101001.111 to the base 2. This is what we have. Okay, so this is what we have. We have to convert this to binary, I mean a decimal. We have to convert this binary to decimal. So here we have 1, 2, 4, 8, 16, 32, 64, 128, 200 is 512. So 512 plus 32, right? This is yeah, this is 64. So 512, 576, 608, and then 608 and 16, 624, 624, and then 608. What's the mistake here? Well, this is 512, 256, 128, 64, 32, 16, 4 and 1. Okay, so now we have 1 plus 4, 5, 5 plus 16, 21, 21, 32, 53, 52, 64, 117, 117 and 512 is equals to 629. So 629 point, this is 0 0.5, this is 0 0.25, so 0 0.75, this is 0 0.125, so it will be 0 0.875. So 875 to the base 10. Okay, so this is how you have to know when you are converting from IEEE 754 32-bit standard. Okay, so now let's look at some of the advantages and disadvantages of floating point standard. Okay, so when you are representing a number using floating point, okay, a greater range of numbers can be represented. Okay, a greater range of numbers can be represented. Okay, greater range. Why is this possible? Okay, well, I'll also include the second advantage, varying precision. Okay, varying precision. Well, what do I mean by this? Well, what I mean by greater ranges, well, think of it. We have 32 bits representation. There, 8 bits are allocated for the exponent. Okay, the exponent part. 8 bits are represented for exponent part. So, which means you can represent a number from 2 to the power minus 127 to 2 to the power 128. This is a huge range. Okay, this is a huge range. Even though this looks like a small number, this is actually a huge range. Okay, this is a huge range. So, since we allocate 8 bits for, especially for exponents, it's a huge number that we can represent using this method. Okay, so you have to keep in mind, okay, the bits allocated for exponent. Okay, if you increase the bits allocated for exponents, the range increases. Okay, the range increases. Okay, what about varying precision? It's about mantissa. Okay, we are allocating in 32-bit system, we are allocating 23 bits for mantissa. Okay, 23 bits, which means we are going for 23 decimal points nearly. Okay, in binary number system. So this means there is nearly 20, we are giving the number perfectly right to the 23 places. Okay, 23 places. So which means this helps the mantissa bits. Okay, if you increase the bits for mantissa, the precision also increases. Okay, the precision increases. This is the main importance or the advantage of IEEE 754 standard. Okay, consider about the 64 bits. In 64-bit system, we allocate 11 bits, 1 bit for sign, 11 bits for exponents, and the other bits, the 52 other bits for mantissa. Look at the precision we have. Okay, when you are doing questions in maths or physics, you just go for 2 decimal points. For example, 734.23. Somebody may ask you to go for 3 places. But here, we have 52-bit for just precision. So you can write a 52-digit number without any issues. Okay, I mean, excluding the exponents. Okay, so this is the most important advantages of floating point representation. But the problem is, even for a small number like 11.10, you will allocate a huge storage space. Okay, these are positives of IEEE 754 standards, and the negatives are storage space. Okay, it takes a lot of storage space. Even for a small number, if you are representing using this method, well, it takes a lot of storage space. Then, due to this storage space increase, the processing time also decreases. I mean, increases the processing time. So, slow processing times. Okay, slow processing times. What are the other disadvantages? Well, sometimes, okay, even though we have an ability to use varying precision, sometimes the number may be too large, and we can have an issue with the precision. Okay, we can have an issue with the precision of the number. Okay, so keep that in mind. Yeah, keep that in mind. Now we'll do an example from 64-bit system. Okay, so let's say we have, well, let's convert this to 64-bit standard. Okay, 64-bit standard. We studied about 32-bit standard. I'll attach the link to the description. But we are going to focus on 64 bits now. Since this is 900, we know 900 to the base 10 can be given as 512, and then we need 256. So 512 and 256 will be 868, and then we just need a 32, right? Yeah, we just need a 32. 512, 256, 512 plus 256 is 768. Yeah, so we need 128. So it will be 512, 256, and then 128 is 896. We just need a 4. Okay, we just need a 4. Well, this is 128, no 64, no 32, no 16, no 8. So this is 900. Okay, so this is 900. No 64, no 32, no 16, no 8, only 4. Okay, so you can recheck this. Okay, 512, 256, and then 128, and then 4. Good. And 0.625 can be converted to binary by multiplying by 2. This will be 1250, this will be 0.500, and this will be 1.000. So 0.625 to the base 10 can be given as 0.101. Okay, I'm just writing these down. Perfect. So that's it. So this number can be given in binary. Okay, this number can be given in binary as 111,000,001,001 to the base 2. Okay, so this is good. Yeah, this is good. Now we can go to the sign, exponent, and finally the mantissa. So what is the sign here? Let's say this is a negative number. Okay, let's say this is a negative number. Well, if it's a negative number, we can clearly see we have to put 1 as the sign bit. Okay, 1 as the sign bit. Then we have to find the power. Okay, the exponent. So let's write down in the standard format. So it will be minus 1.110000101. Okay, so which means we are moving the number to the right towards 1, 2, 3, 4, 5, 6, 7, 8, 9. So it will be 2 to the power 9. Okay, since in 64 bits representation we have 11 bits. Okay, we have 11 bits for representation of exponents. We have to first find the bias number. Okay, bias number by using XSK method. So we know XSK method says 2 to the power k minus 1 minus 1. We have to add this number. Well, here 2 to the power 11 minus 1 minus 1, which is 1023. Okay, so you have to add 1023. Okay, you have to add 1023 to what? 9. So 1023 plus 9 is equals to 1032. Okay, 1023 plus 9 is equals to 1032. So what do we have to do now? We have to represent this in this format. Okay, so 1032 means we have 11 bits. So 1024, and we need only 8. No 512, no 256, no 128, no 64, no 32, no 16, only 8. No 4, no 2, no 1. See, we have 11 bits here perfectly. Okay, now we have to write down the mantissa part, which is this. So 110000100101. How many bits are there? 4, 8, 12. And we know 52 bits are allocated for mantissa, which means we have to put 40 zeros. Okay, there are 40 zeros. Okay, I'm not going to write all those zeros. We have 40 zeros. Keep that in mind. Now, I hope you understand the idea. You just, if the number system changes, okay, the method changes, the standard changes 32 bits or 64 bits, so, or n bits, if they give you in the question, just find the sign bit and then the biasing number by using XSK method, then write down the mantissa. Okay, for 64 bits, they will definitely say you have 11 bits for exponent. Okay, and if they say there are n bits representation, they'll say x bits are allocated for exponent. So like that they will give you. You have to be able to do the questions. Okay, I hope you have a clear understanding. Please let me know if you have any doubts in the comments. I will be more than happy to solve them by using maybe a live stream. Okay, so please let me know in the comments, and that's it. I'll see you in a new video, and stay tuned.
Thanks for watching the 18th video in our number system series. If you found this tutorial on the IEEE 754 floating point standard helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos. Check out the full playlist to master number systems and follow us on Instagram. I'll see you in the next video. Until then, keep learning and stay curious. Bye bye.